So we've talked a lot about how leaving group can impact the rate of SN2 or the rate of SN1. But does the leaving group impact SN1 or SN2? Does it, if it's a better leaving group, does that make it more likely to be SN1 versus SN2, etc.? Turns out the answer is no. It doesn't impact whether something is going to go by an SN1 or an SN2 mechanism. It turns out that a better leaving group blanks the rate of blank SN1 or SN2. What are we putting in those blanks? A better leaving group increases the rate of either SN1 or SN2. And if you hold tight for just 1 minute, we're going to talk about solvent effects. So we just saw in the last video how protic solvents can stabilize the carbocation and the halogen anion intermediates of the reaction, but also how does it impact nucleophiles? So if we think about a strong nucleophile, it would be something like sodium OCH3, which again, when we put into a solvent, it's going to be sodium, the cation kind of floating around by itself, and OCH3, the anion kind of floating around by themselves. So how does a protic solvent impact this? Well, if we had this sodium in solution, if we had methanol as our solvent, the partial minus is going to surround itself around the sodium, which will stabilize that species. Also, the OCH3 will be stabilized in the same way. We have the methanol partial pluses. They will essentially hang out with that negative charge, which stabilizes it. It stabilizes that, makes it of a lower energy. So what we can write this up to kind of put a synopsis of protic solvents. Protic solvents. They stabilize nucleophiles, both anion and cation. And that makes the nucleophiles less strong. So that's polar protic solvents. So not only do they stabilize and make the intermediates of a lower level, which would make the SN1 reaction faster, but also they make the nucleophiles weaker, which also makes them more willing to wait around. So that's one of the reasons why these protic solvents are more ideal for SN1 unimolecular types of reactions. All right, how about aprotic solvents? First of all, what are they? Aprotic solvents lack an acidic proton, which were technically those heteroatom H bonds. So they lack that acidic proton. So what's an example of an aprotic solvent? One example is acetone. So this is acetone. Another example would be dimethyl sulfoxide. This is DMSO, dimethyl sulfoxide. That's the one that kind of the book uses, I'd say, the most often in its reactions. So these are aprotic because they lack any acidic protons. The protons off of here are CH bonds, and really the OH bonds, the NH bonds would be more acidic than most CH bonds. So aprotic solvents have a lot of partial negative charge on an atom. So we can say that this oxygen atom is going to have a lot of partial negative. It would allow that to stabilize cations, but the partial positive that would be on the sulfur atom or even on this carbon atom, so if we had a partial positive here, what did we just learn about CH3s? They delocalize their negative charge to stabilize neighbors. So there's a large partial minus here, but the partial positive is going to be really small comparatively to the ones in the protic solvents. So aprotic solvents have a large, generally they have a large partial minus on, and in this case it's just oxygen, but we'll just say a large partial minus, and they have a small partial positive. So how is that going to impact the nucleophilicity of nucleophiles? So if we had, again, the same nucleophile we talked about on the last video, sodium OCH3, that means you have sodium plus and OCH3 minus. Does this stabilize either of those? And we know in solution we'd have sodium plus, and we can see how the oxygen of DMSO would stabilize that sodium plus. It would kind of orient itself around it like we saw in the last video. We have a partial minus there, partial minus there. So this sodium is being very nicely stabilized by these DMSO molecules. But what about the OCH3? Well, the OCH3 has a full negative charge, and there isn't really a good partial positive on the aprotic solvents to stabilize that. The partial positive on the sulfur is really just too small. It's unable to stabilize that. So what is the effect of polar aprotic solvents on nucleophiles? Well, it stabilizes cations. So we'll actually just kind of write it here. Polar aprotic solvents, they stabilize cations, and that leaves, we'll write leaving, naked anions. So there's nothing stabilizing this negative charge. That full negative charge, the thing that makes that nucleophile unstable and want to react, it's fully on that oxygen atom. So we kind of think of polar aprotic solvents as supercharging nucleophiles. And what did we say about nucleophiles and how they relate to unimolecular versus bimolecular reactions? Strong nucleophiles don't wait around. They react fast. They prefer those bimolecular processes. So essentially, what we know then is that polar aprotic solvents increase bimolecular reaction rate by increasing the strength of the nucleophile. So that's how aprotic solvents differ from protic solvents. So hopefully that was clear. Let me know if you have any questions. All right, so first of all, let's just put this up on the border in your notes. Solvent affects, and I think it should be an A, not an E, because it's a verb. Solvent affects the rate of SN1 or SN2. We'll say and. But it depends on the solvent. This is an and. So it turns out that there are multiple types of solvents. One solvent type is a protic solvent. Protic solvents have heteroatom H bonds. Heteroatom. What's a heteroatom again? A heteroatom is a non-carbon atom. So that would mean an OH bond or an NH bond. Both of those would make something a protic solvent. And it turns out that protic solvents solvate, which kind of means they bind with. So they bind with both anions and cations. Okay, so let's take this a step back. What is a protic solvent? So an example of a protic solvent would be water. That's a protic solvent. Another would be methanol, ethanol. All of these have the heteroatom hydrogen bonds. And what makes that unique about protic solvents is all of them have a strong dipole between atoms that have relatively small radii. So hydrogen, oxygen, relatively small radii, which means that the partial positive that's on that hydrogen and the partial negative that are on that oxygen, they're in small atomic sizes, which makes the charges there's more charge per volume, essentially. So that goes for all of these. There's a partial positive on the hydrogen, partial negative there. The water would have a partial positive on both of the hydrogens, partial negative on the oxygen. So why does this matter? That it can solvate both anions and cations. So what happens in an SN1 reaction? So let's just look at a generic SN1 reaction. And the first step, and what we know about SN1 reactions, we know that tertiary alkyl halides favor SN1 reactions. We also know that they occur when they are in weak nucleophiles, such as, we'll just do methanol here, so just one carbon to the OH. Okay, so what's the first step of this reaction? The first step is that the rate determining step is that the alkyl halide breaks into a carbocation and a Cl minus, or the anion. So why does it matter that protic solvents can solvate both anions and cations? It matters because that means that they stabilize these intermediates. So if this is our solvent, if that positive charge is kind of stabilized by other groups, it's going to make it more stable. So if we have all of the methanol molecules with the partial minuses kind of orienting themselves by that positive charge, oopsie. So all of them are orienting themselves by that positive charge. That stabilizes the positive charge. And they're doing the same thing with the chlorine. They're orienting all of their partially positive hydrogens by the chlorine atom, kind of making hydrogen bonds to it, which stabilizes the intermediates. So what does that do in the reaction? Well, let's think about the SN1 reaction. The first step of the SN1 reaction is rate determining. So we're just going to look at that first step. So we'll put that right here. First step of an SN1 is rate determining, and essentially what happens is we start at the starting materials and we go up to the unstable carbocation. So this is our unstable tertiary carbocation there. So what happens when we have a protic solvent? The protic solvent essentially stabilizes that carbocation. So instead of being at that energy level, so if the black line is with no solvent, we'll say that's with no solvent, the red line may be in a polar protic solvent where the cation and anion are stabilized by the solvent. So essentially it decreases the energy of that intermediate, decreasing the energy of the activation of the reaction, and this speeds up unimolecular reactions. So reactions where we form cations and anions, polar protic solvents speed those things up. So we can say that here. polar protic solvents increase rate for unimolecular reactions. So any time that we're doing an SN1 reaction, it would be best, and sometimes it just makes sense, because in this case, the product here is that solvent actually adding onto it. So essentially, if we're just in that solvent, that's going to facilitate the SN1 reaction best, and then it actually also acts as a nucleophile because it's a weak nucleophile. So kind of take-home message of this part is that polar protic solvents increase the rate of unimolecular reactions. So hold tight for polar aprotic solvents. Getting